So how do you go about naming a polyatomic compound? Well, it's actually just the same as naming an ionic compound with only some minor differences. So to name any ionic compound, you would write the cation, that's usually the metal, first, followed by the anion. And that's actually exactly true with polyatomic ions too. Usually the cation is still a metal, with one exception. That cation might be ammonium, NH4 with a positive 1 charge, right? So that's the only polyatomic ion we have that's positive. Usually, it's actually the cation is just a regular old metal, and the anion, this is usually the polyatomic ion, maybe something like nitrate, NO3 minus, right? Something like that. If that cation is a transition metal, you use the Roman numeral, just like you normally would. So if you have somebody like titanium, you would need to indicate whether you're talking about titanium 3 or maybe titanium 4. So those transition metals that have different charges, you're going to use the Roman numeral to indicate that. So that's an example. The only difference between naming a polyatomic compound and an ionic compound is you don't have to do anything weird with the endings, and that actually makes polyatomic compounds easier than ionic compounds. So if I think about ionic compounds, just for comparison, let's say you had NaCl, right? You would know that this is a sodium bonded to a chlorine, but you wouldn't call it sodium chlorine, you'd call it sodium chlor, and then instead of "ene" here, you'd write "ide" in the naming. So with ionic compounds, we change the ending of the nonmetal of the anion. With polyatomic ions, you don't have to do that. You actually just write the ending as it normally is. The endings are already weird, right? Like sulfate, sulfite. So just keep them as they are. Don't make them any weirder. All right, let's try a few examples. Here we've got a sodium. So I just write down sodium first to name this guy. Bonded to OH. Well, OH is a polyatomic ion, and its name is hydroxide. So I just get to write that name down. Don't have to change any weird endings. I just write down the polyatomic ion name. Here's magnesium. So once again, just a regular old metal. Bonded to the anion, but here the anion is NO3. That's called nitrate. Now you might be wondering, do I have to worry about that too? The fact that there's 2 nitrates there bonded for each magnesium? Actually, you don't have to record that in the name at all. And this is the same as for ionic compounds, right? We know that magnesium has a charge of positive 2. We know that because it's a group 2 metal. And nitrate, we can see right here, has a charge of -1. So that means magnesium wants to give away 2 electrons to get its positive charge. And nitrate wants to gain only 1, so we're going to need to have 2 nitrates to accept those 2 electrons from magnesium. So that means that we need 2 nitrates here, right? So you can tell just from the charges alone that you're going to have 2 nitrates. You don't need to do anything to record that in the name. The name magnesium nitrate gives you all that information that you need. Let's try the next one. So here I have actually 2 polyatomic ions bonded to each other. So we've got ammonium first. And it's bonded to SO4, that is sulfate. And once again, so ammonium is a charge of +1, sulfate is a charge of -2. So that means that ammonium wants to give away 1 electron, but sulfate actually wants 2. So I'm going to need 2 ammoniums in order to get enough electrons for that 1 sulfate to get everything it wants. So that's accounted for just because of the charges. I don't have to indicate that anywhere in my name. Ammonium sulfate is all I need to show that there would be 2 ammoniums for every 1 sulfate. Now this last one is one where I do need to show something because iron is one of those transition metals. Iron can have a charge of 2 or 3. It can lose 2 electrons or it can lose 3 electrons. How do we know which one? Well, we can actually use that chemical formula here to tell. So we're bonded to a phosphate. We have iron, some charge, we don't know yet, bonded to a phosphate. I'm just going to leave a blank there in the middle. but I do know that phosphate has a charge of -3. Well, if there's one iron for every one phosphate, phosphate needed to steal 3 more electrons, then iron must have given away 3 electrons. So that tells me the charge on my iron must have been 3. So this must be iron 3 phosphate. Let's try a couple examples of just going the other way, because I think this is a little bit trickier in some ways. What if you're given the name and you need to write down the formula? Let's try potassium nitrite first. So potassium is K. It's in group 1, so it has a +1 charge. Nitrite is NO2, and it has a -1 charge. So because potassium wants to give away 1 electron, nitrite only wants 1 electron, there's just going to be a ratio of 1 to 1 here. So our formula is actually pretty straightforward. It's just going to be potassium nitrite. 1 potassium, 1 nitrite. Here things get a little bit more complicated. So I have titanium, and I'm told this is titanium 3. So it has a +3 charge. It's going to be bonded to a sulfate. Sulfate is SO4, and it has a 2 negative charge. So titanium wants to get rid of 3 electrons. Sulfate only wants 2. So that means I'm going to need 2 titaniums to give away a total of 6 electrons to 3 different sulfates, each of whom will take 2 of those electrons in order for everybody to get what they want. So to write this as a formula, so it's a funny looking arrow, but that's supposed to be an arrow here. We're going to have 2 titaniums giving away to 3 sulfates. Now, how do I write this sulfate, right? So I've got SO4. I need to say somehow that there's 3 of them. If I just put a 3 here, it's going to look like, I don't know, 43 oxygens or something ridiculous. So what I need to do is actually put brackets around my sulfate. Now this means that I have 3 of the whole sulfate polyatomic ion. So the 2 here means I've got 2 titaniums, and the 3 down here means I have 3 sulfates, and that's only going to work if I put brackets around the polyatomic ion. I don't have to do that around somebody like nitrate, right? I don't have to put brackets around nitrate here because there's only one of them. You only need those brackets when you have multiple of those polyatomic ions. All right, here's another one that we'll see those brackets coming back. So ammonium is NH4. It has a +1 charge. Oxide, well, that's actually not a polyatomic ion at all. That's just regular old oxygen. If I see an oxide or a nitride or a fluoride or a sulfide, right, those are just elements, regular old anions. And oxygen wants 2 electrons. It's in group 16, so it needs 2 more electrons to get a full valence of 8. So it's going to have a -2 charge. So that means I'm actually going to need 2 ammoniums, which each can give away 1 electron, in order to make a single oxygen happy. So I have ammonium. There's my funny looking arrow again. Really should practice drawing arrows better. I've got ammonium, and I need 2 of them. So I'm going to put brackets here, 2 ammoniums, and they will each give away 1 electron to a single oxygen. That gives the oxygen a total of 2 electrons, so it's happy. Last one, calcium. Calcium is in group 2, so it wants to give away 2 electrons. Hydroxide, we can see it right here, has a charge of -1. It wants to gain 1 electron. It's a polyatomic ion. So for calcium hydroxide, I'll have 1 calcium giving away its 2 electrons to 2 hydroxides. So once again, I need those brackets to indicate that this 2 goes with the entire OH, that whole hydroxide. Notice how this would be wrong, right? If I just did calcium hydroxide 2, if I didn't have the brackets there, this formula would mean there's 2 hydrogens and only 1 oxygen, and that's not true at all, right? There's 2 hydroxides, 2 of the whole OH in there. So I need to have those brackets to indicate that the whole hydroxide is what I'm talking about there. And that's how we name polyatomic compounds.